Well, here we are at tutorial 6. Today we're going to be algorithmically generating some small mesh details to place on the surface of another object. We'll just use some little rivet components. Maybe you can think of them as little screws to place on the surface of a hard surface object. Really, today's tutorial is meant to be in preparation for a future tutorial where we're going to be taking actual detailed geometry, such as what we can generate algorithmically, and we're actually going to be baking that surface detail to a normal map. But we haven't gotten there yet in the course. We'll get to this in a few lectures. And so, yeah, this really is our preparation for that tutorial that we'll get to. But today we'll just focus in on generating the detail meshes themselves and just take a look at some different approaches to go about doing that. All right, so I've got Maya open here. I've got a script ready to go, a Python script, and I've got my Maya commands imported. The thing I'll start by doing actually is just quickly creating a plane. We can scale this plane up. Let's go 10 units, scale it by 10, and we can turn off the grid. I'm also going to freeze transformations on the plane. We can drop its subdivisions down to just 1 by 1. That looks good. Can clear history on that. And we can just use this as kind of a placeholder to just show the surface that we're trying to generate details for. Just a 10 by 10 plane, and that'll help us just make sure we get everything in the right place. Okay, so let's go ahead and get started here. We got our commands ready to go. Let's start by just making some notes on what we intend to do here. We'll be creating a function for generating a rivet object, or this little screw object. I'll call it a rivet. So generate rivet. We'll get to that in a few moments. We'll also be generating rows of details. So we'll take that rivet object and generate just a row of details algorithmically. So generate row of details. We'll also do radial details. So we'll do a function for getting details positioned in a circle, and we'll also finish off here by doing kind of like a random detail distribution within a rectangular area. So random distribution. All right, so, and these will be our functions. And I'll put my main section of the script down here where we'll call all the functions that we're using. I'll zoom in nice and close here to make sure this is nice and visible on the video, and we can go ahead and get started. So, yeah, we'll need just a rivet object to get started with. We're going to be using this for the entire tutorial. So let's get started with that. We'll define a new function, call it generate rivet. We're not going to need any arguments passed to any parameters incoming to this function. So we can just go ahead and define that. And in my main section, I'm going to just go ahead and call this function right away. And again, passing in no arguments. So yeah, let's go ahead and start by just creating a new variable. We'll use this variable to store the name of the object we're working with, and that object is going to be a cylinder. So we can just go ahead and call cmds.poly cylinder, and we can set the radius of that cylinder to 0.1 units, and its height to, let's go 0.06 units for the height. All right. Going ahead and running that script. Again, make sure you're calling the generate rivet function. We can see that we've got a little cylinder created here. We'll just quickly go through this. I mean, we've done this process of creating objects using API calls plenty of times. And we've also gone over like selecting components and doing basic modeling operations on them. So I'll go through this fairly quickly, as we don't really need to review that all that much. So we'll start here by just moving the cylinder up so it's sitting directly on top of the plane. So it is currently selected after creating the object. So we can just go ahead and do a cmds.move, 0 on the x, well, that'll be half the height. We'll move half of the height of the cylinder up on the y-axis, 0 on the z. All right, so that gets the cylinder positioned correctly. Can continue on here. I'm going to, actually, let's bring that back. Let's just go into face mode, and we can see that this big n-gon at the top of the cylinder here is face 21. So I'm going to want to select face 21. We're going to bevel it just to get a nice chamfer around the top of the object. So we'll use the format function here in Python to just substitute in the name of the object. That'll be rivet index 0. Again, we've covered this in a previous tutorial. Just the way that Maya gives us information about the object. So that will be the first index of this variable right here that contains the name of the transform node. That we'll just make sure that works right. So that command selects that top n-gon there, and we're going to go ahead and do a cmds.poly bevel and set the offset to 0.05 units. So that gets a nice bevel going on the top there. Let's continue on. And yeah, let's do another selection. Actually, let's just visualize what we're doing here. Yeah, face 41. Again, we want to select that topmost n-gon again. The face ID has changed after the recent bevel. So we do need to do another select. Actually, we can just copy this down here. Don't need to type that all out again. This time we're gonna select face 41. Again, substituting in the same object name here, and with that name or that face selected, we are going to do an extrusion, and I'm just going to shrink, like extrude, and essentially scale that face in a little bit. You could do it with a scale operation, or just use the built-in offset property of the extrusion. So poly extrude facet, and let's go ahead and set the offset to 0.01 units. Let's take a look at what we get there. All right, so that just takes that topmost n-gon and shrinks it in a little bit. We'll do another extrusion and just move the face down a little bit. We can copy this actually, and just do that. And we'll, instead of changing the offset this time, we'll just set the translate y equal to negative 0.01 units. Right, so that'll get us a nice little indent at the top here. And the final modeling operation we will perform with this object is just a bevel on this face ring right here, or this face loop, right? to get something that looks a little bit like this. So we'll just do that algorithmically. We can actually bring this back and just quickly see here that this face loop is faces 62 to 81. Maybe we can zoom in on this a little bit just so it's visible on the video. There we go. The range of faces from 62 to 81. We'll go ahead and select that range of faces so we can do the bevel on them. So same deal as before, but this time we're selecting 62 to 81. Again, substituting in the name of the object. So that'll work for us, and we can do our bevel on this selection. So poly bevel, and I found that an offset, just a very small offset for this bevel, 0.002 worked quite well as I prepared this. Right, so there we go. Just a nice tiny little bevel there, just a nice little surface detail. And that should work nicely for us. Let's finish off here. Let's finish off by selecting the entire object. So rivet index 0. Let's select the entire object itself and just run a soften edge on a soften edge command. Can actually kind of preview what we're trying to do here just so it makes sense. Again, bit of Maya review. See, that's in mesh display. In soften harden edges, the default setting here is an angle of 30 degrees. With the threshold of 30 degrees, any angle larger than that will be softened. Or sorry, any angle larger than that is going to be hardened, actually, and any angle between faces lower than 30 degrees will be softened, right? So if we apply that, you can see that, for example, the small angle between these pairs of faces, these faces all have their normals softened, but the large angle between these faces, for example, has the normals hardened, right? So just to kind of give this a realistic appearance, we can reproduce this. We can reproduce this in Python. Right after selecting the rivet object itself, we can do a cmds.poly soft edge. And just using default settings will be fine. It'll use that 30-degree angle. So that should work just fine for us. There we go. There's our nice rivet object positioned right on top of the plane. Let's go ahead and return. Let's return rivet just so we get that information, specifically the name of the object returned out of the function here, because we're going to need that when we generate either rows or rows of details or radial details or what have you. All right, so with that rivet ready to go, we can move on and start creating a row of rivets. Let's go ahead and comment out that function call. We can bring it back if we need to. All right, so let's move on here and let's define a new function. This is going to be generate detail row, and we're going to be accepting two parameters here, the length of the row as well as the density, or how many objects we are going to distribute along the length of the row. So we'll go ahead and call that function right away, generate detail row, and we'll start with, how about a row 10 units long. That's the width of this surface here. I will put that in as a floating point value just to make sure we are doing floating point division when it comes down to it. And we'll start by distributing 5 objects along that row. So now the general idea here is to use a loop and iterate over the number of objects we're specifying in the density. So that's just an integer. We're going to, well, we're passing in 5 for starters, so we're going to iterate 5 times, and we'll generate 5 rivets. We'll store the name of each rivet as it is generated in just a variable, because we'll need that in a few moments. All right, after creating the object, go ahead and select it. So select detail, and we're going to need to position this appropriately, right? So so far it's just going to be created at origin. We can go ahead and run this and just see that we've got, 5 rivets created. They're all on top of each other there, right? But we got 5 objects created all at origin. Go ahead and undo that. And so what we're going to need to do is do a cmds.move and pick an axis. I'm going to pick the x-axis to do this translation along, and we'll just keep the other translation axes set at 0, but keeping in mind that this does need to be a relative transformation, because, well, we don't want the object absolutely positioned at y equals 0 or z equals 0. So we'll just keep that as a relative transformation to just make this movement relative to the object's existing position. All right, so how far along the x-axis will we move the objects? All right, so we gotta do some math here and figure out where to put the objects. What I'm going to do is actually just calculate a few values outside of the loop, right up top here before we start the loop, actually, because these are going to stay the same and for the entirety of this loop. We don't need to calculate them again during each iteration. So let's just go ahead and figure out these values. We're going to need to know how, what the increment, what the translation increment is for each object, right? So we'll call this position increment, and this is how far to move each object. The distance from the previous objects, right? So this should be equal for every object that we're creating here. It's basically just dividing the length of the row up into equal parts. So, well, pretty straightforward, right? This will just be length divided by density. So, nothing more to it. We'll just do this calculation. We could start actually by positioning each detail as it's created. We'll start by positioning it at position increment times I, right? So this equal increment just multiplied by the iteration that we're currently at. It's a good starting point. And we can see that, all right, so we are off to a good start. However, these details are being generated kind of heading off to the side. They're not, the whole row is not centered on this plane itself. So we're going to have to do a bit more work here and specifically specify the starting position. The starting position for this translation. And we're going to want to put that starting position just on one side of the plane, right? So not starting at origin, but rather at one end of the row that we plan to create. So this should make sense, right? Taking length minus half of the length, right? So length divided by 2. We can actually start with that. This will bring us one step closer. And I do need to bring this into the this movement command. So this will be position start minus, I'll just put in my parentheses here just to make it clear. All right, so that brings us one step closer here. The details are, they're kind of sitting on the surface of this plane now, but it would be really great to get it exactly centered, to get that row exactly centered on the plane itself. So we can finish off just by subtracting position increment divided by 2, right? So half the increment as well. We can think of this as kind of like just a final offset to get that whole row positioned, just half of the increment backwards, half of the increment between each detail. So let's finish that off. So there we go. All right. Pretty straightforward. We just had to figure out the positioning of those details. We can try this for different numbers of details. Maybe let's do 12 details. So that works just fine as well. I don't know. Pick a really simple example. Make sure it works. For odd numbers. For even numbers, right? That looks like it's working as well. And okay, so it looks like that's good to go. We can also use different length values if we wanted, but we'll keep this at 10 units just so that this visually fits on the plane, this plane that we created. All right, so that's good. Let's just group these rivet details once they have been generated, just so we can move them around and keep them all together. So what I'll do is I'll start by just keeping an empty list outside of the scope of the loop. And inside the loop, after creating each object, we'll just after we move it, we'll just take the name of the object and append that to this list. So we'll do a new details dot append, and we'll just pass in detail. And I'll only keep track of the transform node. That's really the only information we need to keep track of here. So detail index 0, just to only pass in the name of the transform node. All right, so that works. And then, so new details, we can print it out actually. Can print that out after creating all the details and see just the name of all those transform nodes displayed in the console. But what we're going to want to do is just do a cmds.group and just group all the objects named in that list, new details. So there we go. If we look in our outliner, we can see that we have group 1 now. This contains all the details we've created. All right, looks great. Let's create a couple sets of details. And right, so this is where the power of doing stuff like this with code really comes in, right? Because we can just specify exactly what we want to generate and just quickly generate that. If you're creating some sort of asset and you quickly need to generate a whole bunch of details, well, this is going to be a whole lot faster than trying to create these by hand. So we'll just put a bunch of different rows of details over to the side here. Perfect. All right, we can comment that out and continue on here. Let's do our radial details now. So same sort of idea here, but this time we're just going to be creating these details and kind of moving them around in a circular shape. So I'll call this generate radial details. It's not going to be a length measurement this time to specify the look of this set of details, but rather a radius. And then we can also use that same density parameter that we were talking about just a few moments ago. All right, so this time, again, we're not going to be doing a translation this time. Let's kind of think about it for a second. We're not translating along a straight line, but rather we're going to be, we're going to be involving some sort of radius of a circular shape, and then we'll need to do some sort of rotation of object, right? If we kind of plan ahead a little bit here, we can think like, okay, so if I want to take a circle, which we can, there's 360 degrees in a circle, and we need to divide that up into an equal number of increments. Well, we can think ahead here a little bit and prepare a rotation increment and have that equal to 360 degrees. Right? Not the length of the line anymore, but rather the 360 degrees of a circle divided by the density, right? This will give us an equal angle measurement by which to rotate each detail around some central position. So that rotation increment will be very useful to us. We'll create our loop again for I in another range. We're iterating over the number of objects we're creating once again. So that's stored in the parameter density. We'll start by again creating another detail object. We'll select that object we just created. And this time we will be doing, we'll start with a movement actually, but this movement is going to be to move the object away from origin to basically to the radius of this circle that we're trying to create. So again, we'll use the x-axis for this translation. We don't need to do anything fancy here. We can just move it out the distance of the radius, because the distance from origin to the edge of the circle will be the radius. So we can just pass in radius for the x value, or the x component of the translation, 0 and 0 for y and z respectively. And again, this will be a relative transformation. So that will work. We can test this out just to make sure we're on the right track here. Always a good idea to check what we're doing. Generate radial details. We'll pass in, how about, actually, if I move these details off the plane, then we can use a radius of 10 units and just see them being positioned in a circle, but on the plane. And we'll go with, I don't know, start with 8. We'll start with 8 objects here, just because that divides out nicely. 360 divides out nicely into 8. Helps us visualize what we're doing. And let's go ahead and run this. And oh dear, that's oh, of course, our radius is 5 units, of course. So let's just set our radius correctly to 5 units, and there we go. All right, so all the objects are positioned out at the extremity of the circle. All right, so there's all the objects positioned out there. But now we need to take care of some rotation around origin by this rotation increment that we've already stored. So let's go right ahead and do that. It'll be done with a cmds.rotate, and we're going to rotate 0 around the x. We will rotate around y, so we'll leave that blank for the time being. 0 around the z, and let's just, before we forget, let's just specify the pivot of this rotation to be origin, because we want to rotate around origin here, not around the pivot of the object itself. All right, and right by how much are we rotating? Well, we'll just rotate around by this rotation increment, which is, well, what we've divided 360 into 8, so this will be a 45-degree increment. So we just need to multiply that increment by I to just get a multiple of that, incrementing as we iterate through the loop. All right, so let's go ahead and run that, and there we go. It's kind of maybe a bit difficult to see. Maybe I'll move that plane out of the way just for a second. So there it is. There's our circle of details, right positioned radially. Let's do that grouping again, just so we get all those details in a group, so we can just move them around. We'll do it the same way we did it before, just by creating an empty list outside of the loop. We can append the name of the transform node we just created to that list, and then just group the contents of that list when we're done. All right, go ahead and run that. Perfect. All right, so there's one radial set. They're pretty small there, but there's one set of details. Let's shrink down that radius. How about to about 2 units? There we go. Working well for us. And maybe smaller and denser. Maybe let's double the number of objects that we're creating. All right, that works very well. And so we'll just move all those radial details off to the side. All right, so, and this is fairly difficult to do. Well, not super difficult, but it would take a little bit of time to just get this transformation right, create a bunch of duplicates of an object, and set the pivot point for your transformation, and maybe if you're working with an arbitrary number of objects, calculate exactly like how many degrees you need to rotate each object by. But again, with a tool like this, which really doesn't take that long to code, we can generate stuff like this very easily. So we'll finish off here with one last function, and this will be for a random distribution of details within a rectangular area. Let's go ahead and we can comment this out and define a new function. I'm going to call this distribute details. So distribute details, and we are going to be using, right, so it's not length, it's not radius this time, but rather it's an X and I'm going to call it a Z boundary, actually, because we are on the XZ plane here. It might be an XY boundary depending on what plane you're working with. I'm going to call this X bound and Z bound. And then, of course, density. We always need that density parameter to show us how many objects to create. All right, we can go ahead and call it right away. So I call this distribute details. And let's keep things simple. Let's just use an X boundary of 10 units, a Z boundary of 10 units as well. And let's do 10. Let's do 10 objects in this case. They're pretty small, and we want to see that they are being distributed nice and randomly around the surface of this plane. So let's create 10 of those to start with, and take a look at how to approach this object creation algorithm. Okay, so it's going to use the same sort of loop that we've been using thus far. We can actually copy this down into the function. So we'll generate a new detail, we'll select it, and then we're going to do a movement. I'll just keep a comment here as we think this through. So cmds.move, and well, this time it's going to be some X translation, no Y translation, because we don't want to move it vertically, rather we want to keep it on the XZ plane. Right, so it's some X translation, some Z translation, and then relative equals true again, because of course this also needs to be a relative translation. Okay, so that makes sense. But how are we going to randomly distribute these details on the XZ plane? Well, let's bring back the random module in Python here. So import random, right? We've used this before when we were doing some stochastic procedural generation, but we'll use the random module again to just give us some random floating point values. And what we can do is, here's a real quick way of getting random floating point values in a certain range. We know that our x boundary and our z boundary are already defined. They are incoming parameters. However, we want to, let's put it this way, right? We're working with this rectangular area here, and x boundary and z boundary they're both positive numbers, and they would describe a rectangle, with x, some x values starting at x equals 0 and extending out to x equals positive 10. Same deal for z. This z boundary specifies the boundary on the z-axis from z equals 0 to z equals positive 10. However, again, we have to kind of offset these values backwards such that they're centered around origin. So we basically need an x offset. We're going to have that equal to x bound divided by 2.0, right? Just to move that specify our offset as half of the incoming x boundary. Same for, that'll be z offset. Same deal here. We're going to have z offset be equal to z bound divided by 2.0. And we'll see in a second why we need these values, but again, the whole point is that we're centering this rectangular area around 0, as opposed to just shooting off in the positive directions along the x and z axes. And so now we can bring in these random values. So before we jump into the loop and try and just blindly position these objects, let's actually print out what we intend to do here. We're going to need, let's start with the x values. We're just going to need to make sure we get x values between, right? So if the x dimension of this surface area is 10 units, then the lower limit of the x value should be -5, and it should extend to +5, right? So we're going to have to manipulate random.random, which is just a random floating point number between 0 and 1. We're going to have to manipulate this value to get us something between -5 and +5. So I'm actually just going to undo a little bit here because I don't want all those extra objects created. But let's go ahead and manipulate this random floating point number between 0 and 1 to get the value we are looking for. All right, so first we are going to multiply by x bound, that incoming parameter. Let's take a look again at the value, and we can see that successfully it scales up the value to be some value between 0 and 10, but we need to bring in that x offset that we just calculated, right? Because again, if we don't have that, then this rectangular area that we're distributing around is not going to be centered around 0. So it'll be random.random times x bound minus the x offset. So now when we run this a couple times. There we go. We got a negative value there. So we are getting our set of values from -5 to +5 in the case of a rectangular area with x dimension of 10. So that'll work for us. Always super valuable to just print out the calculation as we construct it to make sure it is accurate. So this will be a fairly long line of code here, but I've just cut and pasted that calculation in for the x component of this translation, and we're going to do something very similar for the z component, except just going to be referring to the z bound incoming parameter and the z offset that we just calculated here. All right, so if everything is working correctly, we should get a whole bunch of new details generated within this 10 by 10 surface area. Let's run this function a few times. And isn't that neat, right? We can see all these new objects being created here, and they all stay within the surface area that we have specified. Let's make sure this is working for other dimensions as well. Maybe a 10 by 5 rectangular area. All right, so let's run that a few times. So 10 on the x-axis, only 5 this time on the z-axis, and there we go. So we get kind of this rectangular shape, again with the details distributed around that surface area. All right, so that's that method. Again, we can just quickly copy down our code for grouping those objects so we can keep them all together. All right, we can and generate a few groups of randomly distributed details. Maybe let's shrink this down. Let's do maybe a 2 by 2 square, kind of interesting, and maybe a 2 by. Let's do a long, thin collection of details. How about with more details? How about with 20 details distributed along that 2 by 10 surface area? All right, so there we have it. Hopefully that was fun and informative. Some different approaches to algorithmically generating details that you can then place on the surface of a model. And again, in a future tutorial, we're going to take a look at baking those details to a normal map to be able to efficiently render those details out. All right. Well, that's everything for this tutorial. So good luck experimenting with this new information, and we'll see you in the next one.